In the last few examples, we were focused on one thing, the idea of changing of an output based on a change of an input. And those were based on some ground point. So we said, hey, what if we had $200,000 spent on advertising? What if the concentration of a catalyst was 10 milligrams, or the amount was 10 milligrams? We aren't limited necessarily to just changes in the input and output. It's useful, and again, it comes back to that idea that dy dx is somehow an approximation to delta y over delta x. But we can actually go a step further or it's not even further, it's just look at this a little differently and actually create a linear function, so a formula for the complicated function y that's being approximated by something linear, which is what we did here, but we'll write it out just a little bit differently. All right. Let's go back to that advertising problem where we have revenue is a function of the advertising spend, and here are some features of it. So spending $200,000, that's our A. $200,000 in advertising. That's the input, gets us or leads to 1,500,000 in revenue. Okay, so that's the relationship of a function statement. If I plug in 200, I get 1,500 back. If I spend $200,000 in advertising, I will get 1,500,000 or 1.5 million in revenue. We also analyzed earlier this statement about the derivative, which was around 200,000 in advertising. So based on that starting point, that ground point, what can we say? We expect $1.8 in revenue for every $1 in advertising spending. That's the units of the input. Actually, we should have thousands in here. Turns out the thousands cancel, but 1.8 thousand in revenue for every 1,000 extra that we spend in advertising. Okay, so those are two statements that we can use to interpret these values. The question is whether we can use those to generate a formula of some kind. Okay, quick flashback to an alternate linear formula that many students have seen but haven't used as heavily as we're going to want in a second. So just to remind you of this, a little bit of review. If we have the formula y equals m x minus a in brackets plus c, what kind of graph do you get with that? What linear graph do you get with that? Well, let's draw something. Let's draw in a different color. There we go. If I have a graph like this and I pick a point on it, and the point is at coordinate A, C, and the slope of the line is equal to m, this graph would be given by this function. Notice this is not the intercept slope. We can convert between the two. Intercept slope. We can convert between this and the slope-intercept fairly easily, but when you're talking about having one known point on a graph, on a linear function, that doesn't happen to be at x equals 0. This is a shortcut to get you a function y is equal to something that's linear that will guarantee that you go through that point. Just to show how that works, y is at x minus a plus c. One of the ways to look at it is at if x equals a, do we get, so we go out to x equals a, do we get the y coordinate c? Of course we do. Y at a will be m a minus a plus c. A's minus a's cancel, we get 0. The m doesn't matter anymore, and we get C. So that tells us that it's always going to go through the point, whatever this number is here as X, whatever that number there is as Y. Okay, that's the point slope formula. How does that help us work with this kind of function, this revenue and advertising function? Well, if we have our ads, again in thousands of dollars down here, and we have our revenue in thousands of dollars, what are the things that we know based on these two statements about the function? We know that at $200,000 in advertising spending, we are at $1,500 or $1,500,000 in revenue. So there's a point on the graph. I don't know what the graph does, but I know it goes through that point. We also know that the derivative of that point was 1.8. So we can add a feature on here that the slope is equal to 1.8. Now this is perfect because this is exactly what we had in the last slide. Flip back for 1 second. We have a point and we know the slope there. If we want the formula for the line, we can just build it in using this information. So what would we do in this case? Well, our revenue, our linear revenue, approximation, would be given by following this line out forever. So building the entire line based on the point and the slope. Well, the slope is 1.8. Our input is usually called X, but here it's called capital A. Where are we based? We're based at A equals 200. So we have a 200. What revenue do we get when we plug in A equals 200? We get 1,500. So this formula gives us the formula for this line. I get the graph of this line based on the slope and the single point 200, 1,500 for advertising and revenue. The whole point of this exercise is it lets us ask direct questions about new advertising levels. So for example, if we were asked what would happen if we changed our spending to 190. Well, we don't have the function, but we do have the approximation. So actually, that's better yet. Get rid of the, we don't know what it's exactly equal to, but it will be approximately equal to something, and that approximately equal will be based on where we are now and the slope. If we just follow that graph back down to 190, we should get something that's a reasonable approximation for the revenue based on where we were, the revenue we had with 200,000. So here we can bring in our function and the values that we had before, and we're going to sub in that 190 now. And then it just becomes an exercise in calculation. We have 1.8. This ends up being negative 10 plus 1,500, and so that's negative 18 plus 1,500 and 1,482 thousands in dollars of revenue. So where would we expect to end up? We expect to end up at 1,482. So there's a little bit of a break in this graph here. There we go. So that formula lets us sub in not changes, it's a subtle distinction, but before we typed in changes or we used changes in advertising, here we actually have an amount, 190,000. That's how much we will spend. What's the result of that? It's worth noticing this is still a change in here somewhere. It's not the number we inputted, but along the way we said, hey, we're going to decrease from where we were by $10,000. And so delta A, that change in A, does show up in the calculations along the way, but the formula didn't need that number to start with. So subtle distinction from what we've seen before. Here's the formula more generally. Our function, let's say it's back to a function of x, is approximately, so again, we're talking the straight line and then whatever the curve does that has the same slope at that one point. We're going to pick a point for this calculation or this formula. We're going to call it A, and here's f of A. We're going to say the straight line approximation, the blue line, approximates the red line here. Here's the blue line, straight line. If this is going to be a good approximation for values x that are close to a, if we build it based on the slope, so we've had the same slope as the graph itself, with an x minus where are we, plus what's the y coordinate, or the function value at a. Again, the larger that this difference is, so this difference in here in the formula, the larger that difference gets, the worse the approximation will be, because we're going to walk further away. X minus a is the distance of where we are to where we've grounded ourselves and used the slope, computed the slope. So here it's going to get worse and worse. And again, it's important to note that this is basically a change in x. Where did we ground ourselves? Where are we looking? How far are those 2 points apart from each other? That's a difference in x values. The nice thing is those two formulas that we've talked about, f prime of a being approximately delta y over delta x, and this curved function being approximated by a linear function, they're the same formula. They really are. Let's go from this one, and it's easy to show that it goes back to this. If we have f of x is approximately f prime of a, x minus a plus f of a. That's the formula we just derived using the point slope formula for a straight line. Well, what we can do is bring f of a over here, and so we'll have f of x minus f of a is approximately f prime of a, x minus a. So this is our real contiguous function that might be curved. Here's the slope and that difference. Well, wait, difference. Let's put our points on here, x and a. That distance between x and a, we would usually call that a change in x. So we can cancel that out, call it delta x. And what about this part here? Well, we'd have a function, and we have the function values at those 2 points, f of x and f of a. We'd call that distance delta y, possibly. We haven't got y is really in the expression here, but delta f here, or delta y. And hey, delta y. And if we do that, we have delta y is approximately f prime of a delta x. That was one of the forms we saw before. Or we can bring down delta x to the other side. Delta y over delta x is approximately equal to f prime of a. Or dy dx, going back to what we call Leibniz notation. So dy dx is approximately delta y over delta x, or f prime of a. Just working backwards, we can turn that into the linear approximation formula we found through a different route. They're the same formulas, local linearization, tangent line expressions. Those are all the same thing. So keep that in mind as you go through the exercise and you encounter these different names. They're all the same formula under the hood. It's just a question of convenience. Did someone tell me how things are changing, or ask me how things are changing, or did they give me values or ask me for output values? That's the only thing that might make one formula more convenient than the other, but there's no fundamental difference between them.